The hydrophobic interior of the bilayer prevents the movement of ions across the membrane. The only way that ions can diffuse across the membrane is by passing through specialized channels that permit the movement of particular ions while excluding others. When the neuron is at rest, most ion channels are closed. However, a few potassium channels are open, and potassium ions are therefore free to diffuse out of the cell into the extracellular environment. Since only a few sodium channels are open at rest, very few sodium ions flow into the interior of the neuron. If we consider only the potassium ions, which are relatively free to cross the membrane, we notice that the intracellular concentration remains much higher than the extracellular concentration. This is because the potassium ions are pulled by two different and opposing forces. First, a diffusion force acts to pull potassium ions down their concentration gradient toward the exterior of the cell. The movement of potassium ions out of the cell results in a depletion of the internal positive charges, causing the potential to become increasingly negative. An electrical force, produced by attraction of the positively charged potassium ions toward the negative cell interior, generates an electrical gradient that pulls potassium back into the interior of the cell. The diffusion and electrical forces eventually come into balance, and an electrical potential is achieved at which the electrical gradient is exactly balanced by the diffusion gradient. This potential is the equilibrium potential for potassium. At this electrochemical equilibrium, there is no net movement of potassium ions. On average, for each potassium ion that leaves the cell, another returns. The electrical potential across the membrane can be measured using a pair of electrodes. An oscilloscope is used to continuously display the potential difference between the reference electrode and the recording electrode. When both electrodes are in the bath outside of the cell, no difference in potential is measured between them, and the display registers 0 millivolts. However, when the recording electrode enters the cell, the display records a membrane potential of about -60 millivolts. This value represents the resting membrane potential of the neuron, the difference in electrical potential across the membrane during an inactive period.